Why don't we go ahead and get started? So welcome back everybody to EE290C. So yesterday we were just sort of finishing up with discussing about basic transmitters and receivers. Today we'll talk about some stuff about timing. But before we sort of launch into that, I just wanted to kind of get a brief poll of things. So now how many people have actually looked at the homework? Okay, good. So any questions or? Yeah.
Since we know the transmission line has 2 nanosecond delay, how do we get the RC time delay for the?
Well, so there is no real RC. So it's all just reflections. It may happen to look like an RC waveform, but other than that, that's all I will say about. I believe you're asking about the first problem, right? Yeah. So it's not actually an RC. It is actually reflections, but just so happens that it looks a lot like an RC waveform. Okay. So the only other thing that maybe I'll just briefly mention in problem number 2, when I ask you guys to do the termination in part A, there's no magic power supplies coming out of nowhere, so you better figure out how to actually bias things correctly without using any extra power supplies. And then in part D, when I actually ask you to sort of really build it, you should keep track of the fact that, I gave you a limited range of variation on the polyresistor. So you should really try and build it in a way that only compensates for that, rather than just sort of do something that would be a straight, I don't know, just a bunch of variable transistors or something like that, which certainly would work, but was not really the intent of, trying to do this so-called the right way. Okay? So, unless there's any other questions in the homework, what I wanted to just do briefly now was really quickly finish up on sort of the basic transmitter and receiver stuff. And in particular, I had mentioned last time that, I'm assuming that most of you guys remember what StrongArm looks like and sort of how they work. So I'll maybe just sort of quickly draw one and then just kind of ask you guys one quick question, maybe just sort of stimulate some thinking or stimulate maybe some recall about what you might care about in this particular context. Okay, so the most common sort of comparator that you'd see in a high-speed link receiver would again be this StrongArm design, which I'm just going to quickly draw kind of the core piece of it, which looks something like that. So you have your clock, your in plus, your in minus, and then, of course, these are PMOSs. Then up over here, something that looks kind of like a cross-coupled inverter, just with the sources of the two NMOSs being fed by this input differential pair. Okay? And so, of course, there's also some pre-charge devices out over here that just start the output up at a high point. Okay? So again, I'm assuming all of you guys have seen this before. I actually didn't draw all of the pre-charge devices you'd probably want to use here, so keep in mind there's some more. But again, I'm going to assume that you guys have at least seen this once and kind of familiar with how this thing works. If not, go back to some of the old 240 lectures. I think we spent a reasonable amount of time talking about it there. But the thing that I did want to ask you about here is, if you're going to use this thing, remember we said we want to go up to these like 10, 20 gigabit per second, if not even more than that, data rates. Turns out if you start really pushing on those kinds of speeds, you may not actually be able to use this particular type of design. Or rather, there's actually going to be some speed limits that are related to kind of just the way comparators in general operate. Okay? So the question I wanted to ask you guys was, in general, if I just looked at a comparator or really any regenerative structure, what is going to be sort of the fundamental trade-off that you have to deal with in terms of if you were really pushing on the speed as hard as you could? What's sort of the thing that you're probably going to have to give up on? Okay, well there is power, but actually it turns out I'm not even going to throw that one out. Okay, so so power, certainly there's a CV squared F, and if you increase F, power is going to go up. I'm not even going to worry about that. What's the other thing that sort of gets worse as you try and make the comparator run faster and faster?
Offset?
Is it offset? Okay, you said offset hysteresis. It's kind of that, Eric?
Actually, no.
Okay, no. It's related to hysteresis, although I'd claim that's maybe not the first order thing that you might care about.
Or overdrive.
Okay, what did you say?
Overdrive.
Okay, overdrive. What do you mean by overdrive?
Well, so to make it faster, you want to make the input devices smaller.
Okay.
And so in order to get the output to change, you'll need a larger input, and you'll have to overcome the VTH offset from making the devices smaller.
Okay, so you sort of, half of what you said was kind of in the right direction. So let's actually sort of, work something out. So just in general, what sort of sets the speed of this thing? What sets the speed of a comparator?
C by GM.
Yeah, so basically there's essentially a time constant, which is related to the capacitive loading divided by the GM of your devices, right? Now, notice if I look out over here on this regenerative node, your GM is kind of set by your device width, and your capacitance is also set by your device width. Right? So largely speaking, changing the size there doesn't have a huge impact on that C over GM. Right? Because basically, C over GM, if you have just a device driving itself, is largely just FT. Right? So in terms of changing the sizing, the speed doesn't really actually have a big impact. But there was something else that you said which is very directly related to what I'm trying to get at. You said something about input signal swings and things like that.
Condition for regeneration is important in speed. I mean,
So you said the time constant for
the
generation?
swing at the input acts as the initial condition for the regeneration. So
There we go. So you said the swing at the input sort of acts like an initial condition for the regeneration. So what happens if I try and make this thing go really, really fast? What do I have to give up on?
Gain.
Yeah, exactly. Right? Basically what I have to do is if I'm trying to go really fast, that means that the minimum size input signal I can resolve has to be larger. Right? So just to make sure that that's sort of clear to everybody, let's just say, we said that this is the time constant, right? Let's just say we know what that is. There's some regeneration time constant there. Okay? So the question I want to ask you is, if I tell you that you have a certain amount of time to actually operate, or rather, given sort of the amount of time that, or if you wanted to calculate how much time it's going to take you to regenerate a certain input signal, let's call it V in, to a certain swing at the output, let's call that V swing. What is that relationship going to be? In other words, how much time do you need to regenerate an input signal that is V in up to a swing of V swing? What does that equal to?
I think
Tau
it's
times the log of
LNV swing over.
ratio.
Yeah, it's tau times the log of basically the swing you eventually want to get divided by your input signal, right? Okay, so let's actually just throw some numbers out here. So what do you guys think the swing is going to be at the output?
Rail to rail.
Yeah, it's basically rail to rail, right? So it's basically 1 volt as an example, right? Okay, so now let's just do everything in terms of the regeneration time constants. So how many regeneration time constants do I need if I want a V in of 100 millivolts?
2.3.
2.3, right? I need 2.3 tau to get a sensitivity of 100 millivolts, right? Assuming I want a swing of a volt at the output. Okay, well, so what if I want, of course, 10 millivolts of sensitivity? How many tau do I need?
4.6.
Yeah, 4.6, right? And so, of course, if you want to get a 1 millivolt sensitivity, you're going to need 6.9 tau, right? So notice it is a pretty sharp function. But again, if I'm pushing up into these very, very high throughputs, or these very, very high data rates, then it may mean that basically there's only so small of an input signal that I can tolerate. Because if I don't make my input signal large enough, I won't actually be able to regenerate. Right? Because, for example, if I need a millivolt of input signal, it takes me 7 tau. If tau is, let's say, 5 picoseconds, that's 35 picoseconds at least that I need to do it. So I couldn't go faster than something like, 20 or 30 gigabits per second. Right? Of course, depending upon how you phase the clocks, or rather what the duty cycle of the clocks are and things like that. Okay? But keep this in mind, because this is actually sort of one of the key, let's say, fundamental limitations in terms of how you're going to build the link up. Right? So if you remember, we talked way back before about the burr being related to the input swing minus the offset divided by the thermal noise and things like that. Well, don't forget that there is a finite sensitivity you can get in the comparator, simply from the fact that it has to regenerate that small input signal into a full swing thing at the output. Okay? Does this make sense to everybody? Or? Okay, any other questions just on comparators in general? By the way, I'm going to assume that not only have you seen StrongArms before, but you've seen CML comparators as well. In fact, maybe you're even more familiar with those, because it turns out that because of this actual reason here, for example, with CML, you can make that tau regeneration sometimes smaller than you can get it with the StrongArm design. For that reason alone, sometimes people will switch to CML comparators when they're really trying to push on the edge of what's feasible. Okay? So again, any other questions on that, or are we free to move on? All right, guess we're free to move on. So that basically wraps up most of what I wanted to say on kind of the basics of transmitters and receivers. And so the next thing I really wanted to kind of give you a basic overview on was essentially how you're going to do timing in high-speed links. Okay, so as I mentioned before, kind of the goal of the first few weeks of our lectures here, just kind of give you a broad overview of what a few of the different issues are, so that once we start diving into the details of how we build each of the individual components, you kind of have an idea of, at the system level, why do these things actually matter. Okay, so that's why now the next thing I wanted to do is just tell you a bit about timing. Okay, so now the first question, of course, is just why do I need to even talk about timing? And hopefully this is fairly clear. But just to make sure we're all on the same page, the reason you, of course, have to talk about timing is that, if I look at what I actually pick up over here in my receiver, and again, I just draw an eye diagram of what's going into that thing, then as you can probably imagine, if my clock just happens to line up so that I'm sampling, let's say, every bit there and there, well, notice, I don't really have that big of an eye opening there. Right? I've got actually pretty small voltage margins. So just as an example, of course, if I could somehow get my clock to actually sample over here instead, well, hey, my link's going to operate a heck of a lot better right there than it is in that other sampling position. Right? And in fact, you can imagine if my clock is just completely not even related to my data, so that I end up sampling, let's say, one time here, and then another time there, and another time over there, well, that's clearly bad news, right? So again, point here only being that from actually the way the link operates, it's pretty important that you actually put that clock in the right spot. Because if you don't, guess what? You're going to get errors just like you would have gotten errors if the voltage signal wasn't large enough. Okay? So that's really sort of why we're going to be spending some time talking about this. So to kind of, maybe kick off the discussion a little bit, what you'll probably hear about in, let's say, most of the textbooks that talk about timing, specifically in the context of I/Os, is that there's lots of different types of clocking systems out there. Okay? And I'll sort of briefly mention what those are in 1 second. But basically, what all of those different timing or types of clocking end up being related to is just essentially what's the relationship between the clock at the transmitter and the clock at the receiver. And in fact, maybe not even just the relationship between them, but it could also be just whether or not there even exists a clock at the transmitter versus at the receiver. Okay? So to make that more specific, these are kind of, let's say, the 4 basic timing types that you may hear about. And for whatever reason, I guess the people that invented these things were Greek or liked Greek words, so they all use Greek terminology. Okay? So the first type of system is what's called a synchronous system. And that's probably actually the thing that you're most used to. So like, if you ever built a digital chip, then most of those, just about 99% likelihood is that you built a synchronous system. Okay? So what I mean by that is that, at least in principle, both the transmitter and the receiver get the same clock with the same phase. Okay? So in other words, everything is exactly known. It shows up at exactly the same point, same phase, I should say, or same timing at the transmitter as at the receiver. Okay? The next sort of level down from that in terms of, let's say, complexity or things that you have to deal with is what's called a mesosynchronous system. So here, I still have sort of the same clock source, which means it's the same frequency. But from whatever reason, I don't exactly know what the phase is going to be at the receiver relative to at the transmitter. Okay? So this means that somehow I'm going to have to sort of figure out what exactly was that phase difference, and then somehow take care of it to kind of make things actually work out. Okay? The next level in terms of, let's say, again, like complexity is what's called a plesiochronous system. Okay, so what this means is that there's actually 2 completely separate frequency sources at the transmitter versus at the receiver. Okay, so now, not only do you have to sort of figure out what the phase difference is, but there's actually a frequency difference. So that even if you estimated the sort of phase difference once, over time, those things would rotate relative to each other. Okay? The final one, which I'm actually not going to really spend any time at all, is what's called an asynchronous interface. So here you don't really have any clocks that you send back and forth. It's just every time you want to sort of send a token of data, you tell, for example, the transmitter tells the receiver, okay, hey, I'm sending you a token of data. And the receiver says, okay, thank you very much. I received it. You can send me another one. Okay? So as I said, I'm not going to spend a lot of time on this one because, as you can maybe even tell from the picture, that tends to have a lot of overhead in terms of these request and acknowledge signals. So usually that's not a very sort of common way of doing things, at least in these very high-speed I/Os. But I'll mention it here just so you kind of know about it. Okay? And by the way, I guess we do have a Greek person in the room. So was my pronunciation correct? Okay, you don't know. All right. Well, that's how I've heard it. So, I'll assume that that's what it's supposed to be. Okay. So let's just actually start out with kind of the simplest type of clocking system that we could come up with. And I've put this in quotes because, as you'll see in 1 second, if I really tried to do things this way, it's actually kind of more painful than, let's say, the more clever way of doing things. Okay? So let's just say I have this kind of very basic link where I have my transmitter, I have my receiver over here, I have a clock that I'm going to be feeding to both of them. So this is one clock source, meaning it's exact same frequency at both sides. And let's even assume that I did a really good job with the distribution so that it's the same phase at both the transmitter and the receiver over here. Okay, and in fact, there's going to be, of course, some transmission line between the transmitter and the receiver. Let's just assume that that has some delay associated with it. Okay? So the question I'm going to be sort of getting at in the next few slides is just, under what conditions will this particular link, quote-unquote, work? Okay? So to just kick off, let's say, that discussion, I want to ask you this question as if we were in 141. Okay? So when we were in 141, what did we say was kind of the condition from a, let's say, maximum constraint or a cycle time constraint in terms of getting this thing to work?
Setup time constraint.
Okay, so you said there's a setup time constraint. So let's just write that out. What would that be?
So clock Q plus the transmitter delay
Okay, there's a T clock to Q plus some transmitter delay.
plus the transmission line delay.
Right, plus the transmission line delay. Plus
the
what
receiver-
else?
Plus the receiver delay.
Okay, plus the receiver delay. Plus what
the
else?
setup time.
Okay, setup time. And all of that has to be what?
Less than
equal
the
to.
T clock.
Right, all of that has to be less than your bit time. Right? Or the clock period. Right? Okay, so if you were to really do things this way, what's the really bad news about this? Why would this really suck?
Too slow?
Yeah, it's slow. Why is it slow?
Yeah, because you assume that it's not multi-cycle path, so everything should be settled in one cycle. So T bit is really big because P data must be very big.
Right, exactly. Right. So the trick here is that I've forced everything to fit in one clock cycle. So that means that if I have a meter of cable or 0.3 meters of cable or whatever it is, and that takes me multiple nanoseconds to get over, guess what? Your clock cycle time is also limited to something like multiple nanoseconds. Right. So just to give a specific example, if I had 0.3 meters of cable, then I've got about 2 nanoseconds of delay across that cable. Well, that means that my data rate has to be less than 500 megabits per second, right? Yeah.
But if you know sort of what your length of the cable is, isn't it kind of a modulo operation?
Ah, okay. So that's exactly what we're about to do, right? So just like both of you have kind of pointed out, what you really do is you say, well, okay, that really sucks, but I don't really exactly have to do that. What I can instead do is just say, well, okay, look, I can actually launch multiple bits down this cable at any one time, right? I can send I can just stream it so that there's data just flying down that cable, right? And I actually make it so that there's sort of multiple clock cycles that it would take to get data from the transmitter over to the receiver, right? So indeed, if I do that, then I can actually break the constraint that we just wrote 1 second ago, okay? So indeed, what you really will do is you'll make it so that there's multiple bits on the line at any one time. So just to give you guys kind of an idea, or actually maybe I'll even ask you guys. So what do you guys think would be kind of like a typical number of bits to be on the line at any one time? Just ballpark. And of course, tell me how you got there.
Few tens.
Okay, a few tens. How'd you get there?
So you have 2 nanoseconds.
Okay, so let's say we have 2 nanoseconds of cable delay.
Right. And then if it's 10 gigabit per second, then it's 10 symbols per nanosecond.
Okay, great. So if I have a 10 gigabit per second link, then that means that I basically have 20 bits on the line. Right? So notice 20 bits on the line, that means, things are really packed into there. Right? You've really got things flying down that line at a much, much faster rate than what you could have gotten by actually sort of waiting for everything to settle out across the entire line. Right? So that's actually indeed a pretty common number. Now, Igor sort of actually already mentioned this a little bit, but what's the real trick to making this work? How do you really make sure that this works out? And I'll maybe label a couple of things here to make it, let's say, obvious. What's really critical in terms of getting this to actually function correctly?
So know that the delay of the line inside what module, the time period you want your clock to be.
Right, exactly. So the whole trick here is that basically you have to make sure that the clock at the receiver, which I've just called clock 2, lands at so-called the right place. Okay? So you guys have both already said that it needs to be sort of modulo some number of the bits. Turns out it's slightly more complicated than that. So let's actually work out what it really is. Okay? But that basic idea is indeed the right idea. Okay? So let's just indeed say that the delay of my line there is 2 nanoseconds. And what I want to do is figure out what are the allowed bit times that I can use. Okay? So to answer that question, I claim there's actually a few other things that we need to know. So what else do you guys think might be important in terms of figuring that out? Can you immediately calculate it just from everything that I've given you here, or what else is important? Or rather, what else could screw you up?
Delays of the transmitter and the receiver.
Okay, so let's even ignore the delays of the transmitter and receiver. I mean, you're absolutely right. But let's even ignore those for 1 second.
Hold time?
Okay, hold time. It is related to that, but so it's actually another 141 thing that we talked about. It is related to hold time, or rather, the
Skew.
okay, skew and jitter, right? So if there's any uncertainty in the clocks, both of those are going to eat into sort of your so-called timing margin, right? And I'll draw a picture that'll sort of make that clear in 1 second. But so you certainly need to know what is the skew, and again, I'm just going to label the clock at the transmitter and the clock at the receiver. You certainly need to know the skew between clock 1 and clock 2, okay? You also need to know the jitter. Now, it turns out, and I'll explain maybe in a couple more weeks why this is the case, you need to know the jitter not only on clock 1, meaning the jitter on the transmit clock, but you also actually care about what's the jitter between clock 1 and clock 2. Okay? So just to be clear, there is actually a distinction between jitter that's on the transmitter versus jitter that's on the receiver. Okay? And like I said, I'll explain in a couple more weeks why that's the case, but just intuitively, on the transmitter, if you have jitter, it not only sort of shifts when you've sent a particular bit, but it can actually change kind of the waveform that you send. Right? Because you can imagine if I have, let's say, one cycle that's a little bit late, and the next cycle that's a little bit early, I'm actually sending a narrower bit in the first place. Right? Whereas on the receiver, if I move the clock around, all I'm doing is literally changing the sampling position. Okay? And those two are actually slightly different from each other. Okay? Turns out there's one more thing that you actually do kind of need to know, which is a little bit subtle, and most people don't talk about. So what's actually the other thing that you really do need to know if we want to figure out exactly what's the bit times that are allowed? Any guesses?
Phase difference between clock 1 and clock 2.
Okay, you said the phase difference between clock 1 and clock 2. I'd kind of call that the skew. So I think we've got that one covered. I'll give you guys a hint. So take a look at that eye diagram, right? What if I told you the eye diagram looked different? In other words, what if I said the eye diagram, instead of looking like it does there, looked like this, right?
The edge rate, kind of?
Yeah, so it's not actually just the edge rate. To say it more generally, it's really the shape of the waveform, okay? So again, to make that sort of clear, what I'm really saying here is that imagine that I have something that just magically, looks really, really clean, right? So that my eye diagram looked something like this, which is kind of implying that the bits that I'm transmitting have a fairly sharp rise time, are completely flat, and then a sharp fall time again, right? You can imagine that what's, let's say, a good time for you to sample here, and let's just arbitrarily say that this would be kind of the good region there. That might be very different than if, for example, my shape of the waveform is going into the receiver. They might actually look something like this instead. right? And by the way, that shape that I've drawn there is not, sort of arbitrary. If you actually took your bits and passed them through a first-order low-pass filter, this is what they'd look like. Okay? So you can imagine here, now it's not, let's say, quite as obvious what the quote-unquote good region is. Okay, maybe it's, I don't know, something like that, right? So again, this is something that's kind of subtle and people don't really talk about it. But actually, the shape of the waveform is pretty important in terms of figuring out where is kind of the right place for you to place the sampling edge. Okay? And in fact, if you take some communication systems and things, courses on things like that, they'll actually even tell you that there's a lot of sophisticated algorithms you could come up with that would tell you to figure out where exactly to place the sampling edge based on the shape of that waveform. Okay? So we're not going to spend a ton of time on that in this class, but you should certainly keep in mind, because it's one of those, let's say, second order kinds of things that actually can have an impact on you if you're not careful about it. Okay? So now I think we can actually answer sort of my original question, which was, oh, did I skip something? No, I guess not. Okay. So now I think I can actually sort of answer the original question, which is, okay, how do we go about figuring out what are the allowed bit times, given the fact that the delay of my data is 2 nanoseconds? Okay? So the way we're going to do this is sort of as follows. So let's first, just to make our life easy, assume that we have square bits. Okay? In other words, it has a perfectly sharp rise time and a perfectly sharp fall time. Okay? And I'm also going to assume that the sort of the net timing uncertainty, and by that what I mean is the skew plus the jitter, is going to be plus minus 50 picoseconds. Okay? I've just arbitrarily made that number up, but obviously you can calculate what it would really be. Okay? So if I make that assumption, then what we basically have to do is make sure that our received data, or rather the received clock, lands at a good point inside of the data. Okay? So let me just kind of draw a picture that will maybe make it clear what I mean by that. So let's say that I sort of look at the data at the transmitter. So at some point in time, I'm going to be launching that data off of the transmitter, right? And then sometime later is when it's actually going to show up at the receiver. Okay? So let me sort of draw that eye diagram right there. Okay? So ideally, since I said I had these square bits, my eye diagram would look something like that, right? But remember I said I had some timing uncertainty? So that kind of means that, in either one of these directions, it may arrive actually a little bit earlier or a little bit later, right? And that could happen on both of the edges. Okay? So if this is, let's say, the nominal bit positions, then what I'm basically saying is from there to there is 50 picoseconds. And also from there to there is also 50 picoseconds. Okay? And of course, from these nominal positions, that's my bit time. Okay? So now if you kind of look at this picture, what we're basically saying is that as long as my clock arrives anywhere within kind of this window that I'm highlighting right here, then I'm kind of okay, right? That's kind of an okay spot for me to land on. Okay? So what this basically tells you is that if I just line everything up on kind of, as we were saying before, modulo the number of bits that you have, and what you basically say is that what you kind of want is nominally for it to land at kind of n times t bit, but then just away from exactly that number of bits by however much kind of timing uncertainty you have on one side. And on the other side, if this is, let's say, n plus 1 times t bit, right, you want to make sure it arrives kind of before by a timing uncertainty from that other side as well, right? And of course, you can just keep repeating this because I'm going to have this happen again over here and over there and so on and so forth, right? So there's basically kind of these repetitive regions of goodness where if my clock lands there, then I'm in good shape, right? Does this kind of make sense to people, or? Okay, so now I'm going to show you kind of a plot in 1 second of what this actually implies about what are good so-called bit times. But, intuitively, can you guys sort of think about what is this going to imply in terms of what are valid, cycle times for me to use? Or to say it another way, can I use just any cycle time that I want? Or is there only going to be certain cycle times that are good? What do you guys think? Can I just arbitrarily pick, some bit time out of thin air and say, yes, it'll definitely work on this particular link? Or no? No, right? Because if I just arbitrarily pick some bit time, then I could just happen to get unlucky. And with this fixed 2 nanosecond delay, your clock could land right on the bad region, right? So if you actually work it out, what ends up happening is that for these given conditions, basically there's always these bands of clock periods that turn out to work, okay? So the way, just to sort of help you guys interpret what this plot is saying here, if there's a blue line, then basically anything under that blue line means that this is a good cycle time for you to use, okay? So what you can kind of see here is that if I wanted to have 6 bits on the line at any one time, then I'm allowed to use anything between about, 280 picoseconds up to about 320 picoseconds under this particular conditions that I've used here. Okay, then similarly, if I say, well, okay, no, I don't want 6 bits on the line, I actually want 7 bits on the line, well, see there's this break in the middle here, right? That break in the middle is just associated with, if you use that particular bit period, you'd always land in the bad regions in terms of timing, okay? And what you can see is as you increase the number of bits on the line, kind of the regions of goodness keep getting smaller and smaller, right? Because kind of intuitively, think about that if you have more and more bits on the line, it's more and more likely that as you keep adding another bit, you happen to just hit one spot that's bad, right? Does that kind of make sense to people, or?
If you don't have jitter, then I got confused because I think the narrowing of this band is caused by the jitter, right? Yeah.
It's caused not just by the jitter, but it's also by the timing uncertainty. Okay?
Yeah, but if you don't have timing uncertainty, you almost always can guarantee you can sample the center of the eye, then you can basically have infinite small beats, right? Is that right?
Well, no, because don't forget, even if I land here once, the next time around I'm going to be shifted slightly, right? So
Okay.
if I'm shifted slightly, then I'm actually going to hit kind of a bad region pretty quickly, right? In other words, it really says that there's a pretty narrow region over which you're allowed to actually make this thing land in the right spot.
Yeah, because what I mean is that you can never go to like t bit equals 100 because the jitter itself is 50 already.
Oh, of course.
Right,
So
so-
certainly having 100 picoseconds is not going to be allowed. That's certainly the case. But notice, even at about 100 and something, I'm already having this very, very narrow region where it might actually work. Okay. So again, the point here is really that if you're going to do something like this, it's pretty nasty, right? There's a wide region of stuff where it just doesn't happen to really work out the way you want it to. Okay. Does this make sense to everybody, or?
So what's the source of timing uncertainty that you're talking about here?
It could be either skew or jitter. Right, so I just drew it, all of it's kind of being together, but I'm basically saying it's either skew or jitter that could cause a problem there.
The phase of clock 2 is basically fixed with respect to clock 1.
Well,
Fixed as a
so
nominally
there is going to be
fixed.
some skew there, right? But I'm assuming if that skew is unknown. Right, so if I don't know what that skew is, then I sort of have to budget for it on either side, right? Question, Linkai, or?
I have a similar question. So the 50 picoseconds here includes only the source, or?
I'm sort of saying lumped, it's both the transmitter and the receiver relative to each other.
Because that might cause a different effect here, right? Because the transmitter might just make the bit time actually shorter, but on top of that, the receiver might actually also vary.
Yeah, no, so what I'm saying here by the net timing uncertainty, because I happen to choose square pulses, which means that I basically have no channel at all, in that particular instance, the fact that I have a narrower bit is no different than moving the sample point. Okay? What happens is when you actually have some filtering, if I make the bit narrower, then everything gets messed up, right? But if I have, I chose the simple example just so I didn't have to deal with that. But it's a good question. Does that make sense now, or? Okay. So, what do you guys think we're going to do to try and fix this? What's kind of an easy thing you can do to fix it?
Randomly move the clock.
Okay, you can independently move the clock. Turns out there's even one more thing before that that's easier.
Next slide.
Okay, well, yes, it is the next slide. So the next slide is what's called source synchronous clocking. Okay? So the idea here is actually very, very simple. It just says, look, instead of trying to, magically line up that delay on the clock or the bit time versus the delay on the clock, instead, why don't we just make it so that whatever clock I use at the transmitter, I'll just send it down something that looks exactly the same as the link I'm using for the data, right? So if I do that, then now kind of like the clock and the data are sort of lined up with each other, right? They're both traveling kind of with the same delay on them, okay? So now if I do that, and notice there is this extra little delay here that I've added onto the clock that I'll ask you guys about in 1 second. But if I do that right, then basically now I can actually make things work all the way from DC up to just whatever I would have been limited by in any case. So either timing uncertainty or voltage margin or whatever it is, right? Because now I'm just making it so that both the clock and the data kind of travel together, right? So if I set up the right relationship in the first place, it'll stay the right relationship all the way at the end, okay? Now again, there was only that one minor caveat of I needed to add this delay over here. So what is that delay? Why do I need it? And what's the right value for that delay?
Setup time of the flip-flop.
Say that again.
Setup time of the flip-flop.
Okay, is there anything else in there that you care about? And by the way, remember, I'll go back to my eye diagram over here. Remember there's, even though I gave you some peak numbers for the jitter, really it's kind of a random thing. So you always want to be sort of as far away from the edges as you can be. Okay, so if you want to be as far away from the edges as you can be, where do you want to put the sampling clock?
Center.
Yeah, you want to put it in the center of the data, which, assuming I have a square data pulse, is, what would the delay be that I need?
Half a bit.
Yeah, I need a half bit time delay, right? So in other words, that delay that I need there should be t bit over 2, okay?
There's also the clock to Q delay on.
There is indeed also the clock to Q delay of the flop. There's, or rather to say it more generally, there's sort of the aperture of the flop. You're absolutely right. But I'm ignoring that for now just to kind of keep the discussion simple. And we'll again talk about in one more second actually sort of how you'd fix that particular problem. But turns out even before we get there, there's even some other problems that we're going to run into with this particular thing. Yeah?
But that is assume that you are sampling the... Okay, that's true. Sorry, yeah, forget my...
Okay.
So that's if you also sample the center of the data and the transmitter, then you don't have this. But it's not the case because you have a flip here.
Okay. Okay, good. So, source synchronous clocking is indeed actually sort of a nice way of solving this particular problem. But there's a couple of issues that we need to be a little bit careful about here. Okay, so the first one is that notice the way I've drawn this, I've got a clock and then I've got a link, right? So I probably don't want to have to send a clock with every single link that I'm using, right? Because that's already a factor of 2 overhead that I'm paying, right? So instead what you will typically do is you'd bunch a bunch of these links together, right? And then send only one clock for kind of a group of those links, right? And again, that's purely just to minimize the overhead both from a power and area standpoint as well as from a sort of board real estate standpoint. Okay, so typically you'd maybe send one of these clock lines for, I don't know, every 8 or 10 or maybe even 16 data links, okay? So now the question that we should sort of obviously jump out at you is, well, okay, that's great, but what happens if this data line doesn't match that data line? Or this clock line doesn't match one of those data lines? Or even better than that, if you don't exactly get that delay just right. Or in fact, you just change the frequency and you have to readjust that delay, right? And by the way, in terms of not getting that delay right, you can imagine that's probably built with some sort of active circuit or something like that. So if process changes, if voltage changes, if temperature changes, all of those things could shift that delay around, okay? So in general, this is indeed sort of, structurally how things look. But if you really want to do it, what you'll actually end up with is something that looks a little bit more like this, plus, just a couple of, let's say, small, quote-unquote, things that I'm going to add to it, okay? So the first thing to notice here is that now what I've done is I've actually taken this clock, and I've allowed myself to put in a new or separate delay for each one of the data links, okay? So why do you guys think I did that? What's good about allowing myself to have different delays for each one of the links?
And account for the mismatch in the...
Exactly, I can account for the mismatch between the different data links, right? So now the way you actually will do this is not only will you allow yourself to have different delays, but if I just nominally set those delays and I don't really know what the mismatch between things is going to be ahead of time, then I still sort of have a problem, right? So in fact, what you really will do is something like the following. What you'll actually do is sort of take the clock, take the data, somehow you'll detect kind of what the difference between them is. You'll somehow sort of filter out that so-called error signal, and then use that to go back and actually adjust the delay you're using. Okay? And in fact, you'll do that probably on each and every single one of your data links. Okay? So again, the basic idea there is that if I have a way of detecting what the error in my clock is relative to my data, and then sort of filtering that out, I can go back and actually adjust what the delay should be. Yeah?
Do you want to put that before the flip-flop? Or is it actually after?
Oh, actually, fair enough. You're right. I probably should put that before the flip-flop over here. Good catch. Okay, there might even actually be a way I could do it after the flip-flop, but conceptually you're correct. So you probably put that before the flop. Okay? I'll actually show you how you really do it in 1 second, but conceptually you're absolutely right. Okay? So if you look around at sort of the literature, or you just sort of hear these things, this is usually what's called per pin skew compensation. Okay? And again, this is actually a pretty important technique these days because remember, if I've got like 8 or 10 of these data links that I want to share for one clock link, pretty darn tough to match 8 links perfectly to each other. And in fact, even if I have like, 1 or 2% variation and those links are long enough to begin with, remember, I've got many, many bits flying on that line at any one time. Right? So even a couple of % variation could be a very big percentage variation relative to your bit time. Okay? So actually having the capability to sort of tune the clocking on each individual link is a pretty important sort of, let's say, technique to enable you to really get to these very, very high throughput types of designs. Okay? So in general, this type of sort of, let's say compensation or clock adjustment is quite powerful because if you do things right, you can really get rid of almost all of the deterministic kind of errors. Okay, now that of course relies on you building, let's say, a good detector and things like that, but indeed if you do that right, then all of the kind of deterministic errors you might have, all the skew and things like that, you really can actually get rid of by doing this. Okay? It turns out that this particular structure can actually even filter out some of the jitter. Okay, so I won't spend a lot of time on that today because that's something that I want to sort of talk about in maybe another week or so. But just the intuitive kind of explanation as to what's going on there is that basically notice the clock that I'm using here at the transmitter eventually shows up over here at the receiver as well. So you can imagine that if just from whatever reason that clock kind of jumps and stays there for a long time in that new position, then eventually that jumped phase will show up over here at the receiver too, right? So it's as if the receiver doesn't really see any change. Now, that's good news, but as you can maybe already tell from my description, that doesn't work at all, let's say, frequencies, right? Because if I jump one cycle and then jump back to the next, and it takes me 10 bits to actually get that clock over to the receiver, then by the time the clock gets to the receiver, it may not actually be lined up with what's going on in the data anymore. Okay? So again, that's something that I'll talk about a little bit more later on, but it turns out these source synchronous structures can actually filter out some of the jitter that you'd get on this clock. Okay? This make sense to people, or? Yeah.
If you have that detection filtering function, why do you still need to send a clock data from transmitter?
Ah, okay, that's a great question. You don't necessarily have to. Okay? But as I just mentioned, and actually as we'll talk about in 1 second, turns out that when you build this thing, most likely the overhead that you'd get from doing this will be smaller if you really have this clock versus if you don't. Okay? And we'll actually talk a lot more about the detail of how you build these kinds of things. But you're absolutely right. You don't necessarily have to send this clock anymore. Okay? So in fact, that's a great, sort of lead into this next thing that I wanted to say. Yeah?
So actually, don't you want to track the jitter from the transmitter so that you sort of you're sort of moving with the clock in some sense?
That's right. So in fact, that's exactly what this type of configuration allows you to do. Okay, now in principle you might say, well, but if I have this filter thing, this feedback loop, then why doesn't that also track the jitter? So it turns out that does track some of the jitter. The problem is, anytime I have a feedback loop like this, I can't actually make it track all of the jitter. There's only a certain bandwidth of jitter that I can actually track. And if you do something like this, the bandwidth you can track turns out to be higher. So again, this is something we'll actually talk a lot more in detail about when we really get into how you build these kinds of systems and what are sort of the things you need to keep track of. But from a high level, that's kind of the trade-off that's there. Yeah?
At first pass, it looks like the clock stays sort of with the same delay as the data, and so...
Okay, so almost.
Yeah.
So it almost is the same. The only minor caveat is that there is actually some mismatch here, right? Let's say in the transmission lines right there. And okay, I'm compensating for it with these delays over here. But remember, none of these things is ideal, right? So if there's any residual mismatch or residual modulation of those things, then the clock that actually shows up over here will not be exactly the same as the clock that sort of went through this path. But you're absolutely right. If you kept those exactly aligned with each other, you'd basically be getting rid of all of the jitter that you would have had on this original clock over here. That's absolutely correct. Turns out, by the way, again, these things are even slightly more complicated. A lot of times, you wouldn't actually send a clock at the full data rate. You might actually send it at a sub-harmonic of the data rate. So let's say that you had, 5 gigabit per second links here. You might only send a 500 megahertz clock. And then that means that you have something on the other side that's multiplying that clock up. That's sort of creating an additional filter over here, which means there may again be differences in those two paths. Okay? And again, we'll actually talk a lot more about this when we really get into the detail of how you build these. But you've actually got exactly the right idea, which is as long as you can keep the sort of the clock, let's say the transfer function from clock jitter from here to there, the same as the transfer function as jitter from here to there, you're good. You'll kill all the jitter. Does that make sense? Or? Great. Other questions on this? Or? Okay, so as we were kind of starting to dive into already, in general, if you sort of think about what it is that you're really trying to do, is you're really getting to what's called a CDR. Okay, so CDR just stands for clock and data recovery. So conceptually, all that this, something that a CDR is doing is just trying to figure out what is the clock phase I should be using to receive my data based on the data itself. Okay? So as we've already sort of talked about, I could have a system where I only adjusted the phase of some clock, which would mean that I need a reference in the first place. Or I could even have a system that would just generate its own clock completely, right? In which case I don't really need a reference directly. Okay? So there's kind of several advantages of using something similar to a CDR. And people don't always call it a CDR. They sometimes call it, as I said, per pin skew compensation or periodic timing adjustment or things like that. But they all kind of boil down to the same thing. So the advantages versus just having, like a fixed timing link like we had before is first of all that you don't really have to perfectly match the delays and the paths between all these different things. Right? Which is just another way of saying that if I have a mesosynchronous system, meaning the phases are unknown, I can use these loops to go and sort of figure out what the phases actually are and still get the whole system to work. Okay? In fact, not only that, it would allow me to use completely separate frequency sources in the transmitter and the receiver. You can imagine if I have a really big backplane, or in fact, even something, an Ethernet or something like that, pretty darn hard to get the, the little crystal that's in my laptop to be the same as the crystals in your laptop. So having something that sort of figures out, okay, what is that frequency difference, and then allows the two of us to talk to each other, pretty darn important, right? So indeed, that's another sort of advantage of using these clock and data recovery types of systems. Okay? The only caveat, of course, is there's no free lunch, right? You actually have to build this thing. And as we'll see when we really get into the detail, there's generally some overhead involved with actually building those loops up. Okay? Turns out it also actually places some kind of requirements on what type of data it is that you're sending and receiving. Okay? Because basically, as we'll see in 1 second, in terms of data, you really only get timing information when the data makes transitions. Right? If there's no transitions in the data, then it's pretty darn hard for you to figure out what is the right place for you to actually sample it. Because if it's always the same thing, who the hell cares? You just keep sampling it anywheres, and you'll get the right answer, right? Okay.
Questions.
Yeah.
So if the crystals are different, occasionally does the transmitter have to tell the receiver to, sorry, you have to wait an extra, you have to slip a cycle?
Great question. So indeed, that,
Or
so
conversely,
it depends on the system that you're building. So if I had something where I'm really continuously sending data, then you can imagine if my frequency at the transmitter is just 100 ppm greater than the frequency at the receiver, and I'm constantly sending data, okay, well, at some point I'm going to be hosed, right? Because the thing over here is faster than the thing over here can sync it, right? So the way you indeed handle that is you basically build in what's called sort of idle periods into what you're sending, right? So either you code what you send at the transmitter, so there's always kind of these idle characters that the receiver can just gobble up and throw away, or you move to something like a packet-based system where you say, okay, look, the longest packet I'm ever going to send you is so big, so that you can always have idle, waiting times in between for the receiver to kind of catch up. Okay, and I'll actually have a slide on that, in 3 or 4 more slides that we'll talk a little bit about more in detail. But that's a great question.
I mean, you're not really going to be clocking at the crystal frequency, right? So wouldn't you?
But even if you multiply it up.
But couldn't your CDR though correct the? I mean,
okay, so I'll show you exactly what the problem with that is again in like 3 or 4 more slides. Okay, so if it's not clear then definitely ask me again. Okay, but there is one limited case where you can do exactly what you're saying. But in general, that turns out to not exactly work out. And you'll see why I say that just a few more slides. Okay, so maybe I'll just keep you in suspense for a little bit. Okay? Okay, so before we kind of dive into that, what I want to do is just sort of briefly show you just conceptually how is it you go about building a CDR. And there's really actually nothing too magic here. Okay, so what you're really doing when you build a CDR is you essentially say, okay, I take my input. I'm going to be receiving that input with, with some clock. What I really want to do is take that input and then figure out what's the difference in terms of quote-unquote phase between that clock that I'm using to sample my data and my data. Okay? So that PD there, that just stands for something like a phase detector. Okay? Once I figure out sort of what that error is, I'm just going to take it and pass it through some filter, okay, which is usually referred to as a loop filter. In general, it's going to be some sort of low-pass kind of thing, okay? Or in fact, more generally, it's an integration, because you want to try and drive that error to 0, right? Then once you do that, you basically pass that into some block that just somehow adjusts the phase, right? And that block, depending upon how exactly you build it, may have a reference clock going into it or not. Okay, so as an example, if you were completely generating your own clock, then inside of that phase adjustment might just be like a voltage-controlled oscillator or some other sort of oscillator, where you're changing its frequency based on the control. Or if you're just sort of, if you just really want to be catching only the phase, then you'd really just be using this to adjust the delay of some clock signal you already had. Okay? So there's kind of just a couple things I wanted to mention here. We already said the phase adjustment could be a voltage-controlled oscillator, could be a voltage-controlled delay line, could be any one of a number of other things. Okay, and again, we'll actually talk in a couple of weeks about exactly what would be inside of that and how you'd really build it up. Okay. In terms of the loop filter, as I said, it's usually an integration. But it turns out what you really need to put inside of there heavily depends upon what is the system you're operating in. So for example, if all you need to deal with is just static skews between the transmitter and the receiver, that may drive you to build one kind of loop filter. But if instead you have to deal with 2 different crystals, that would drive you to build a different kind of loop filter. In fact, depending upon how far apart those crystals need to be from each other, or could be from each other in terms of frequency offset, again, that may drive you to actually design the loop filter in a slightly different way. Okay? The final thing I wanted to just sort of spend a little bit of time on, and we'll kind of draw a couple pictures, is just how do you actually do this phase detect on data versus a clock? And again, the key there is really that you only get updates, you only get phase information on the transitions. Okay, so hopefully it should be sort of intuitively clear why that is, but if not, what I want to actually do is just show you a couple of examples of how you actually build those phase detectors. Okay? So the first one is what's known as a Hog phase detector. It's just named after the guy who I believe invented this. Actually, it's probably about 30 or 40 years ago. It's also sometimes referred to as a linear phase detector, because as you'll see in 1 second, kind of the signal that you get out of it is linearly proportional to the phase error between the clock and the data that you're receiving. Okay? So the way this thing looks is something like the following. Okay, so you take your input data, and at first what I'm going to do is just actually send it through 2 flip-flops. Okay? But notice the second flip-flop, I've put that little bubble there. I'm going to make that one actually clocked off of the negative edge of the clock. Okay? Then what I'm basically going to do is do an XOR between essentially the input and the output of both of those flops. Okay? So it's going to look something like that. Okay? So it's going to turn out this signal over here is going to be what's called an up signal. And this signal over here is going to be what's called down. Okay, so up and down sort of implies which direction should you be moving the clock phase. So up would mean like make the clock earlier, and down would mean make the clock later. Okay? So to see how this thing works, it's usually easiest to just kind of draw a couple of waveforms. Okay? So let's say that this is my input voltage. It just has some transition right there like that. Okay? And let's say that initially my clock, from whatever reason, is lined up like this. Okay? So, what would my up signal do with this type of input, or with this Vin and with that clock? What would the up signal do? By the way, in general, when I have these XORs like this, where I have an XOR at the input versus the output of a flip-flop, when is the output of that XOR high?
In a transition.
Okay, you said about a transition. Maybe I just want to say it slightly more generally. In general, when is the output of the XOR high?
When they're different.
Yeah, when they're different, right? Okay, so basically, what you said is obviously correct. I'm just pushing it in a particular way. Okay, so what this basically says is that up, whenever Vin is different than the flopped version of Vin, it's going to be high, right? So what is up going to do with this particular input waveform?
0 always.
Is it always 0? And okay, so I guess I have to be more, precise. There's a little difference there.
Okay.
So what is it going to do?
It's going to be high in that point, and then it's going to
Right.
be 0.
So it's going to have this little glitch right here, right? Like it's going to be high only for that small little window right there, and then low the rest of the time. Okay? How about the down signal? When is that going to be high?
Near the downward edge of the clock.
Okay, so you said something about the downward edge of the clock. That's actually right. What's the starting point? Like when does
the
it?
Same as the.
Is it the same?
When up goes down.
Ah, there we go. It's actually when up goes down, or really more precisely, it's when the clock goes high, right? Because once the clock goes high, this Vin transition shows up over here, but hasn't shown up over here yet, which means that this XOR now sees the difference, right? So if I draw that in, that will just look like this. Okay? So now the way you use this is really, the information is kind of represented in the widths of those pulses, right? So in other words, if I have this really narrow up pulse followed by a really wide down pulse, then that's kind of saying that you should move more down than you move up, right? So you can imagine if I just took the up and the down and I integrated them both and I then did the subtraction, then on the net this would tend to push you down, right? It would tend to push you sort of to move that clock in this direction, okay? So it turns out that if you do this type of phase detector, where the place at which you'll end up quote-unquote locking, meaning the point at which you'd set the clock to, is essentially when the up and the down pulses are the same as each other, right? So if I draw that, kind of on this picture, and I'll try and be, let's say, slightly more precise, roughly speaking, that lands you somewhere like this, okay? So that if I looked at that up and down pulse, that would be my up, and that would be my down. Okay, and again, the idea there being that the up and the down pulses, if those widths are the same, then that means that I'm actually locked. Okay, and in this particular example, if you sort of think about it, that means that this delay right here should be half a bit time, right? Because that delay is the width of the up pulse, and then t bit minus that is the width of the down pulse. And the only way to get them to be equal is if it's half and half, right? So I'll just mark that right here. That should be t bit over 2, okay? So this is actually kind of, let's say, one of the most basic ways of building these types of phase detectors, but turns out this particular implementation has some things that are kind of bad about it. So what are some bad points about this particular implementation?
Q delay.
Ah, okay. So it turns out this particular implementation doesn't compensate for clock to Q. Right? Because there is indeed an extra clock to Q delay to get that signal through the flip-flop versus what happens when the transition just goes into that XOR. Okay, so indeed that is actually a problem with this particular design. Okay, that's actually a very good one. Anything else that's kind of nasty about this?
It's not duty cycle corrected.
If clock is not what?
Duty cycle corrected, or I mean it's not 50-50.
Ah, okay. So if the clock doesn't have 50% duty cycle, that also will cause a problem. That's actually a fairly common problem for almost all CDRs, but that is actually correct. Anything else?
Well, if one wants to operate on negative clockage, maybe inverter will cause some?
Oh, you're just saying that if I actually put an inverter to cause it to be the negative edge of the clock, then again I have some uncompensated delay. That's true. By the way, again, almost all CDRs have that particular problem, but that is actually true. By the way, there's actually something much more nasty about this.
What about the metastability?
No, there is that, but that's actually not what I'm getting at. I'll give you guys a hint. What is that thing?
Not full swing.
Ah, that's not a digital signal, right? Or at least it's not a very good digital signal. Because it's just gone through my channel, it's gone through all kinds of reflections, it's gone through God knows what, right? So that thing may look nasty, right? In fact, it may even be really small, right? It may only be a couple hundred millivolts, right? So if I'm going to try and do things this way, that means that this XOR right there has to resolve that tiny little input signal and make it look really like a digital input, right? That's kind of crappy. So in other words, if you really wanted to use something like this, what it usually forces you to do is put what's called a limiting amplifier in front so that it just takes whatever the analog signals are and rails them out to some full swing thing that you can then use to actually do the phase detection on. And trust me, that usually costs you way more power than the entire rest of the link. Okay, so that's usually not how you want to do things. In fact, maybe 10, well, yeah, probably about, this stopped being used probably about 20 years ago. Okay, for about that, for roughly speaking that reason. Okay? So instead what you will typically do is what's known as a bang-bang phase detector, or it's also known as an Alexander phase detector. So the big difference here is that instead of you getting sort of linearly proportional information about how wrong your phase error is, or how big your phase error is, here you only get what direction should you go. In other words, if you're too late, the only information you get is that you're late, but you don't know how late you are. Okay? So the way this thing works is something like the following. Basically take, in addition to your main data converter, take and this one, generally speaking, what I mean by edge would be that it's clocked by the inverse of the data clock. Okay? If I have like a full rate system, meaning that my clock rate is the same as my bit rate. Okay? But really, to be more precise, it just means the edge clock is half a bit time away from the data clock. Okay? So what this now allows me to do is something like the following. So let's assume that my data clock is actually early. Okay? And remember, my edge clock should really be sort of just positioned always half a bit time away from the data clock. Okay? Well, in that case, what's going to happen is, let's say that I actually have a transition. In this particular case is an example from 1 to 0. Okay? Well, notice if my clock is a little bit early, then what I'll see is that the sample that I got on the edge will actually match up with my previous data sample, right? Whereas if it's a little bit late, instead of matching up with the previous data sample, it'll actually match up with the next data sample. Right? And the trick there is just that as long as this thing crosses through 0 at that half bit time away, right at 0 is where you decide, were you more like the previous bit or were you more like the next bit, right? So the trick here is that I can now, just based on looking at whether my edge sample is similar to the previous data bit or the next data bit, I can decide whether or not I'm early or late. Okay? So much like we did with this, I just basically average out those early and late signals until I get the same number of earlies as I get lates. If I do that, then I should be kind of right on that center spot there. Okay? Does this make sense to people, or?
Yeah, so the up and downs are deciding if you actually had a transition.
Right, so that's absolutely right. Not only do you have to look at sort of whether or not your edge is the same as the data, but it's only in the condition that you actually had a transition that you should even pay attention. Right? Because obviously, if my data was flat, then my edge is going to be the same as both the previous and the next, right? Which basically means it's useless. Okay? So just like with this one, in fact, in general with all CDRs, you really only get information whenever there's transitions in the data itself. Because otherwise you really don't have any timing information to work off of. Okay? There's actually one other thing which, again, I had mentioned is sort of subtle that has to do with this. So can you guys think of anything else that, might cause this to not exactly work the way you want it to?
Rise and fall times?
What about the rise and fall times? Okay, if the rise and fall times are different, you could actually get some weirdnesses going on there. In fact, I'll say it more generally. It really, again, depends on the shape of this waveform, right? Because it could just so happen that at half a bit time away, that waveform doesn't actually hit 0. And if it doesn't, then if I do things this way, I won't actually lock to exactly the right spot. Okay, so again, if you go and you talk to like the communications guys, they'll tell you this is a suboptimal timing recovery system because it doesn't guarantee that you're at the maximum or the minimum bit error rate. Okay, and it's absolutely correct. So again, it's something kind of subtle and you won't hear talked about a lot in kind of even the high-speed links community. But indeed, that is an issue to be aware of. Okay?
I suppose if you knew your waveform shape a priori, then you could...
Right, so if you knew your waveform shape a priori, then you could try and shift your position of the sampling edge relative to the waveform shape to figure out exactly the right spot. But again, you can imagine that gets dicey pretty quickly. Because the waveform shape depends exactly on the channel conditions. It depends exactly on what your circuits look like, right? Indeed, what you're saying is correct, but that's a bit tricky to do. Okay? By the way, we'll talk about actually some other types of clock and data recovery, but this one here is probably by far the most common. Because it does actually tend to work reasonably well, despite these kind of, let's say, second-order issues that don't give you exactly the right sampling phase. Okay? Okay, so I don't think I'm actually going to spend too much time on this because we're going to spend a lot more time on it later. But there's a bazillion different ways you can do the phase adjustment. As I said, you can basically build something that either controls the frequency of an oscillator. You could change the delay of some inverters or some other delay cell somewhere. Related to that, of course, is whether or not you're effectively building a phase lock loop, which generates a new frequency, or a delay lock loop, which is just changing the delay off of some clock signal. The way you control those things, of course, could be either digital or analog. You can imagine that with that linear phase detector, it's much more convenient to do things in the analog domain. Whereas with this bang-bang phase detector, it's more convenient to do things in the digital domain because you're getting bang-bang signals anyways. Right? And by bang-bang, that just means 1, 0, or up-down. Right? Okay, so as I said, we'll talk a lot more about that later, but really all of these sort of phase adjustment things just boil down to either adjusting the delay of something, the frequency of something, or actually both. Okay? So the last kind of couple things I wanted to spend a few minutes on were actually related to some of the questions that people were asking about earlier. So if you really go and you start building these systems that have these CDRs in them, then indeed one of the nice advantages is that you can actually use different crystals at the transmitter versus at the receiver. But this turns out it has some, let's say, interesting system implications. So if you sort of think about what you're doing, what you're basically going to do is, if I have one crystal over at the transmitter, then every, let's say, so often I'm transmitting the equivalent of 10 bits at a certain frequency. Okay? That frequency is set by the crystal at the transmitter. Well, that goes over through the transmission line into the receiver, right? Well, this receiver over here, through its CDR, it's going to figure out what was that clock that the transmitter was using. In other words, what was that F1 that the transmitter was transmitting at? But I actually may have to transmit it or get it into my chip, not at this F1, but actually whatever clock frequency my receiver chip is using, which may be F2. Okay? So what you always end up having to put in that kind of situation is the so-called elastic buffer, or FIFO. Okay? So FIFO just means first in, first out. In other words, it's just kind of this buffer where you're taking in data that's being sent, shoving it into the buffer, and then hopefully there's periods of time that you're not transmitting any data where you can grab it back out of the data, out of the buffer, and you know that you're not going to lose any data that the transmitter may have been sending. Okay? So the whole trick there is that basically what you have to do is you have to make sure that this buffer is deep enough so that over however many maximum bits the transmitter is sending in any one given, for example, packet, you can store all of those bits and still make sure, or rather store enough of those bits that if the clock on the receiver was slower, it wouldn't basically run out of time to actually catch all those bits. Right? Because you can imagine, let's say that this is 10% slower, then that means that buffer needs to hold 1 extra bit for every 10 bits that the transmitter sent. Right? In other words, if I had a 100-bit long packet, then that buffer would need to be 10 bits long so that after the transmitter is done, the receiver could grab the rest of the bits and not actually lose anything. Right? Does that make sense to people? Or? Okay. So the other thing, of course, is that the CDR has to be able to track the maximum frequency offset. Yeah, question?
What if F2 is running faster than F1?
Okay. If F2 is running faster than F1, then actually life is, in some sense, what this buffer is doing is slowing down F2. Right? In other words, what it's going to do is instead of F2 continually grabbing things, at some point it'll say, no, wait, you have to skip 1 bit here so that you can actually get the real data bit. Right? So in other words, that's why this thing kind of works in both directions. It's not only making it so that you can buffer things long enough, it's also saying, no, wait, you don't actually have a real bit yet. Yeah?
But this sort of only works in communication systems where you just have to get the bits across. It might not work in, like, say, audio systems where, like, you're sending samples to, like, say, be played back and you actually need
Not necessarily. So the whole trick here, what you're kind of getting at, is that anytime you have to do this, it's going to insert some latency. And that's absolutely correct. Right? Now, by the way, even in audio systems, the good news is a few kilohertz is dog slow compared to just about anything on the chip. So even if I have, 20-ish nanoseconds or 100 nanoseconds of extra latency, not that big of a deal. But you're absolutely right. This has a direct implication on the latency. And that is indeed sometimes why people will say, okay, I really don't want to deal with this because it is going to cause me some extra latency. Now, here's where I think I'm going to answer Stephen's question, or maybe I'll get Stephen to answer it for me. So you originally asked me, well, wait a minute. This CDR is regenerating F1, right? So why don't I just use F1 in the entire rest of my chip? So now, you tell me, why can't I do that?
Well, I feel that there's some startup time before you have a correct clock for the CDR to work. But I mean,
That's
if you
true.
have that training period, I still see that you can do it.
Okay, I'll give you a hint. The reason is actually written on the slide. I just haven't highlighted it yet.
Is it the tracking?
No, it's not anywhere down here. So what's the reason you can't do that?
Your logic's listening to other links.
There we go. There's other links on the chip, right? I don't just have one link. I've got 20 or 30 or 100. And each and every single one of them might have a different clock frequency. So which one of them do I use to clock the rest of my chip? Does that make sense now?
No.
Okay, so
wait, you're talking about the chip 2 is talking to the other links.
exactly. So chip 2 is not only talking to chip 1 over here, it's talking to chip 3, chip 4, chip 5, chip 1000, and each and every single one of those may have a different clock frequency. So the problem is I have to basically go to this one clock domain just because otherwise, there's 1,000 different domains for me to choose from, and any single one of them will be different than the other one. Right? That's really the reason. So you're absolutely right that if I really just had one clock domain for my entire chip, then I could indeed just take this clock that's recovered from the CDR and use that to clock the entire rest of the chip and completely forget about this junk.
Yeah, but if you didn't have those other links, like if it was just one, 2 set chips that need to talk to each other.
That's right.
Then it's
That's
fine,
absolutely right. So like I said, there's a limited set of circumstances where what you said is absolutely correct. It's just that in general, and in fact usually, I actually have a lot of other links that I'm talking to, especially in these backplane types of applications. If you're talking about something like, let's say, a wireless link where, there's one thing just talking to one other thing, then it maybe would make some sense. Although even there, I probably have lots of different wireless links and I'm talking to multiple different partners. Even there, it may not be so straightforward to do. Yeah?
Just in general, why don't you just use one single crystal for the entire board?
Because then I have to route that thing over the entire backplane.
But then it's kind of slow signals.
Maybe, maybe not. If I want a 400 or 500 megahertz crystal, then that's not that slow.
Okay.
And if I go over the entire backplane, by the way, my phase will be completely unknown. And then what could happen is if the delay mismatch between one point on the backplane is big enough compared to the other point, you can actually get things that look a lot like frequency differences just because it took so many cycles to get over here versus over there. In other words, you start getting exposed to the long-term drift of the crystal.
Okay.
Well, and also this might be like a fiber optic link somewhere.
Yeah, right. I mean, even better, right? If it's a fiber optic link and this thing is across the Atlantic Ocean, sorry, I'm probably not going to want to route the crystal over there. Or even your laptop with an Ethernet cable, right? I probably don't want to be sending my stupid crystal over to your laptop and then locking your laptop to my laptop, right? I mean, okay, maybe that's not so bad, but I'd probably come up with some clever, weird things that would happen because of that, right? Does that make sense? Or? Okay. So just a couple other sort of really quick things before we wrap up for today. In the context of blocking links, there's just a couple of other things that you'll probably hear or come across that I wanted to just maybe clarify. So the first is you'll probably hear a lot of discussion about parallel links versus serial links. Okay? Now, it turns out there isn't really that big of a difference between them in terms of how you'll build things. There's just kind of, let's say, a logical difference between them that people tend to enforce because, from whatever reason, at an architectural level, they want to think of it one way or the other. Okay, so to clarify what I mean by that, let me just sort of draw an example of what is considered to be a serial link versus what's considered to be a parallel link. Okay? And remember, in both serial and parallel links, you might actually have multiple of these on any one chip. Okay? So in a serial link, let's just look at an example that has two serial links. Okay, so I have, of course, my transmitter, my receiver. I have another transmitter, and then another receiver. Okay? So in a serial link, the whole trick is that let's say that I was sending some bit sequence that was 1, 0, 0, 1, 1, 0 on that upper link. And on the lower link, I was sending 0, 0, let's make it 1, 0, 1, 1. Okay? So in the serial link, remember, these transmission lines may not be exactly the same as each other. They could actually be slightly different, right? They could have some pretty significant skew between them. So in the serial link, the whole trick is that over here, when it comes out at the receiver, in terms of the alignment between those data bits, I may have the thing that comes out on the upper link shifted relative to what comes out on the lower link. Okay? In other words, when I've added these x's here, what I've basically said is that this thing on the lower link, I'm allowing it to come out 2 bit times earlier than what came out on the upper link. Okay? In other words, I'm not enforcing any relationship between the alignment of the bits on this lower link and the upper link. Okay? So really the only difference between that and what's called a parallel link is that now in the parallel link, I'm actually going to enforce that relationship. In other words, if I was sending something like that on one of the links, then in time, what I want to come out will also still be aligned between them. So let me just draw it really quickly, and you guys will see what I mean by that. Okay, so basically what I'm going to do is if each one of those was kind of built the same way as I built the serial link before, I'm going to shove those pieces of data into some other box. And what that box is going to do is realign things so that coming out, all of the bits will still be aligned in time. Okay, so in other words, when I got a 1 here, I should have gotten a 0 there. When I got a 0 here, I got a 0 there, and so on and so forth. Okay? So again, this is really just a logical abstraction that once these things are used afterwards, you know that the time relationship between the different links is maintained. Okay, whereas in the serial link, you're just saying, forget it. I'm just going to allow you to have completely different timing on one stream of data versus the other stream of data. Okay, so that means that basically, if you actually cared about this one being lined up with that 0, in the serial link, that's not guaranteed anymore. Okay, so in other words, you should really treat it in the serial link. Only this stream of data should be sort of related to itself. Whereas in the parallel link, you're allowing the timing relationship between them to actually be maintained, and therefore you can use the data sort of in parallel like that. Does that kind of make sense to people? Or? So again, just keep this in the back of your head because there used to be these long discussions about serial links versus parallel links. They're basically the same thing. It's just kind of this logical difference between them. Okay? So I think we're basically out of time for today. We'll just kind of quickly finish up with this next time, and then we'll actually start talking about some of the equalization structures that we'll be using a little bit later on. So see you guys on Thursday.
Do I answer?